In question 24a, we have a circuit including a thermistor, and in part 1 we're asked to find the mean drift velocity of the free electrons in the thermistor. Well, this uses the equation that current is equal to the number of charge carriers per cubic meter, the charge carrier density, times the cross-sectional area, times the mean drift velocity, times the charge on a charge carrier. Okay, in this case, the current is equal to the potential difference over the resistance. So we can rearrange this expression to give drift velocity is equal to I over NAE. And then we can substitute in for this expression to give V over NAER. Then the potential difference is 3 volts. The charge carrier density is 5.0 times 10 to the 25. The cross-sectional area, 3.8 times 10 to the minus 6 square meters. The charge on the electron, 1.60 times 10 to the minus 19 coulombs. And the resistance is 100 ohms. This gives a drift velocity of 9.9 times 10 to the minus 4 meters per second. In part 2, we're told the thermistor is now heated. We're to describe and explain the effect on the ammeter and voltmeter readings. Well, the resistance of the thermistor will go down, so the current and therefore the ammeter reading will go up. This is due to the increase in charge carrier density in the thermistor as it is heated. The voltmeter reading wouldn't change. We're told the supply has negligible internal resistance and there are no other components in series with the thermistor, so all of the supply potential difference is lost across the thermistor. In B part 1 we have another circuit, and we're told that the contact X is placed in the middle of a wire which with 1 meter of length has a resistance of 16 ohms, meaning half a meter will have half that resistance of 8 ohms. We're told the voltmeter reading is 1.2 volts. Where to find the internal resistance of the cell? Well, initially we can find the current, which is V over R. The voltage is 1.2 volts. The resistance is the 2 ohm fixed resistor plus 8 ohms for the wire. This gives a current of 0.12 amps. Then we can use the equation that the terminal potential difference is equal to the supply EMF minus the current times the internal resistance. So we can rearrange to get V minus epsilon over minus I is equal to the internal resistance. Then we can put in the figures. 1.2 volts terminal potential difference minus 1.5 volts EMF over the current we've just found of minus 0.12 amps gives a resistance of 2.5 ohms. In part 2 we have a graph of potential difference against distance along the wire, where to explain the variation of V with D in terms of the current in the circuit. Well, as the distance D increases, the total resistance of the circuit will increase, and as current is potential difference over resistance, the current will reduce. Using terminal potential difference is equal to EMF minus the current times the internal resistance, the lost volts across the internal resistance, this term here, will reduce as the current reduces. This gives a higher terminal potential difference.